We discussed about a Las Vegas probabilistic algorithm for selection problem in the previous lecture. Las Vegas algorithms are those probabilistic algorithms returning correct solution for every instance to the problem. The agenda for this lecture is to discuss a Las Vegas algorithm for the sorting problem, and we are going to see a randomized quicksort which is a Las Vegas algorithm. What is sorting? Given a sequence S of n elements, find an ordered permutation S prime of the elements in the sequence. Formally, this is how we can define the sorting problem. Given a finite sequence of elements, find an ordered permutation, an arrangement which is ordered. Example, given a sequence of 9 numbers, we may be asked to find an ordered permutation where the numbers are arranged in the non-decreasing order. Here the required output is this, where you can see that it is non-decreasing order. It is not increasing, because if you look at these two numbers, they are the same. So to be precise, we can say that it is arranged in the non-decreasing order. It is not that a minimum of order of n log n work is required to solve the sorting problem. It is mathematically established that any correct algorithm needs order of n log n work to be done. And there are many sorting algorithms. Some of them have complexity order of n log n, and others have complexity order of n square. Example, merge sort is an example algorithm with n log n complexity, and bubble sort is an example sorting algorithm with complexity order of n square. And the quicksort algorithm proposed by the Turing Award winner Charles Anthony Richard Hoare is known to be good for many applications. So we are going to see the quicksort algorithm, and later we can see how we can apply probabilistic method to get a Las Vegas algorithm. So what is quicksort? It's basically a divide and conquer based sorting algorithm. I hope you remember the basic control flow followed by the quicksort procedure. Anyway, we can see it. It do necessary rearrangements to divide the sequence, given sequence, into two subsequences, so that once you divide it into two subsequences, no effort is required to combine the sub results to yield the result for the original instance. Unlike in the case of merge sort, where you are dividing the list into two, sorting them separately, and then you need to merge them. Two different sorted lists needs to be merged. But in quicksort, the division is made in such a way that you can separately sort the first and second list such that no further merging is required. So, given a sequence S of elements from index I to j, to start with I will be 1 and j will be n. The idea is to select an element p in the sequence as pivot and then rearrange the elements of S such that the elements placed before p are less than p and the elements placed after p are greater than p. And this is what we discussed in the previous lecture as pivoting. And once you do pivoting for a selected pivot, you are dividing the list like in the middle you have p occurring, maybe many occurrences can be there, but all the elements before p are less than p and all the elements after p are greater than p. So, you can sort them separately, no need to merge, and that is how you are doing the pivoting operation. And recall that the function pivot is discussed in the previous lecture can be used to implement quicksort. We can try to understand more about quicksort using an example. Suppose we are given with a sequence of say 9 numbers like this, and what you can do initially is you apply quicksort on the sequence with every number from 1 to 9, and then what you do is you call the procedure that we discussed in the previous lecture, pivot bis, with S as the sequence and the first element of the sequence. Always whatever be the sequence given to the quicksort, now it is from 1 to 9. So, the first element in general it could be from I to j. So, you take Si, in this case 1, S1 as the pivot, and what pivot bis will do? It will rearrange the elements of the given sequence and return a new sequence, say S1, such that in that sequence the pivot which is 31, because S1 is processed as pivot, is placed in the required position, and before 31 you have all elements less than 31 and after 31 you have all elements greater than 31, and the first position in the second set is returned as L and the last position in the first sequence is returned as K. So, now you can easily see that no need to worry about this part which is already sorted. You can separately apply the quicksort. Now, first on the red sequence, that is you apply quicksort from 1 to 3 on this sequence S1, it should be S1, and after that what you can do, if you apply this, it will recursively sort this part and you will get S2 as the result. And now what you can do is you apply quicksort in this subsequence from 7 to 9. Not that you are passing this subsequence from S1. Okay. Now, if you do that, this will again get sorted. So, it is 47, 58, 85 is what you need, and now you see that no further merging is required, it is already sorted. So, this is basically what a quicksort algorithm is doing to sort a given sequence of elements. Now, you can formally look at the procedure as an algorithm, and what is it doing first is it checks whether j minus I, that is the number of elements, suppose the number of j minus I is 0, means no elements, or j minus I is 1 or 2, very small number of elements, maybe 10, then this particular algorithm is asking you to do insert sort on that. Okay, if the number of elements is very small, don't go for the quick sort, no need to do that, you just go for the insertion sorting. So this is the procedure for insertion sort. If the number of elements in the sequence is very small, you go for insertion sort. Otherwise, if it is large, what you do is you are selecting pivot as the first element of the given sequence. Then this is what we did. We are applying pivot bits, getting I and k and l, and then you are calling quicksort in the red sequence, that is this, from I to k, in the green sequence, that is from L to j. That's what you are doing, and we can prove that the average case complexity of the quicksort algorithm, now it is deterministic, is n log n, and the worst case is n squared. And the worst case happens when you give it a sequence which is already sorted, either in the non-increasing order or in the non-decreasing order. In that case, every time, because you are selecting the first element of the subsequence, it will divide the sequence into two, where in the first sequence only one element and in the other sequence n minus 1 elements, and that is how it divides, and that is the worst case instance to this problem. And whatever be the pivot that you select in a deterministic algorithm, one can come up with a input instance which will cause the algorithm to take order of n square time. So the quicksort is taking n log n time for the average case and order of n square in the worst case. So this is a case where we can try to get a Las Vegas algorithm. A Las Vegas algorithm is trying to steal some time from the best case and give it to the worst case to make both the time maybe n log n. So we can apply randomness here to get a Las Vegas quicksort algorithm whose expected time of execution is n log n for all instances, that is for both the average case and worst case. So what is it basically going to do is, rather than selecting a particular element, it is going to select an arbitrary element from the sequence. That is the only difference. So here is that procedure. The only difference is that rather than selecting a particular element from the subsequence, it first uniformly at random selects an index from I to j, random index value, and pivot is selected as the element at that random index. That is the only difference. And we can prove that the expected time of execution of this randomized algorithm is order of n log n, regardless of what instance you are passing to it. This is the Las Vegas algorithm because this algorithm is going to give you the correct result for any instance. And unlike the deterministic quicksort algorithm, no one can create an instance to cause the Las Vegas quicksort algorithm, this algorithm, to take quadratic time, order of n square. Whatever be the input, it doesn't matter. You can prove that the expected time of execution is n log n. But in the case of a deterministic algorithm, it doesn't matter whether you select the first element as the pivot always, or any element but which is fixed. Then you can come up with an input instance which will cause the algorithm to take order of n square. But that is not possible with this Las Vegas algorithm, because you don't know what index the algorithm is going to decide. It's uniformly at random, and that is the thing that allows you to get this complexity for all instances. So with this we are finishing this lecture. Today we looked at the quicksort algorithm, which is proposed by Tony Hoare, and whose average time complexity, average case complexity is in the order of n log n, and the worst case complexity is order of n square, quadratic. So there is a natural tendency for people to try for a Las Vegas algorithm, and they tried and they got a Las Vegas algorithm, and what they did is they have selected the pivot element uniformly at random. So basically the quicksort algorithm is using the pivoting procedure for dividing the list into two, such that once you divide it into two lists, there is no need to merge. The pivoting will arrange the elements in such a way that no merging is further required. With this we are finishing this lecture. Thank you.